Welcome back. I hope you enjoyed the YouTube video. So now let's delve into making a link between circular motion and simple harmonic motion. So just to recap, we've got some little particle and it's constrained to move in a circle. We're thinking of it moving anti-clockwise. And what we're doing is we're viewing our particle from the side. So if we do that, then we won't actually see it going around in a circle, we'll just see it going up and down. But let's analyze this a little bit more and see where the simple harmonic motion comes in. Okay, so from rotation in classical mechanics, we know that the angle that our particle makes with the positive x-axis, if we call that theta, it's equal to the angular frequency times time plus alpha. That's what we've got over here. So the angular frequency, omega, and alpha are both constants. So it's just our time that's making our angle change linearly. But what we're particularly interested in, if we imagine, so now we're having to change our point of view a little bit. Imagine that we're looking up from here and we're trying to figure out what we see. Well, what we see is the particle moving backwards and forwards along the x-axis. What exactly is it? I mean, how does that motion happen? Well, we can do a little bit of work. We know that we have a right angle triangle here. And we know that this angle here is theta, and there's our right angle over there. So we could work out what that side length there is if we knew what the radius of our circle was. So we would know that at a particular time, the distance of our particle from the origin along the x-axis must be given by our cosine of theta. But we know that cosine of theta is just cosine of omega t plus alpha. So this might not be super easy to visualize, so I've put together another little GeoGebra applet which you can play with. Let's just have a look at that. Okay, so here we have our little particle. It's starting off at an angle of alpha from the x-axis at time t equals 0, and you'll see that the value of the x-coordinate at time t equals 0 is 0.87. And you could in fact work out from this that our angle alpha needs to be 30 degrees. So what I'm plotting on the axes below my little diagram is time and x displacement. So the diagram that has the circle has x and y, but now I'm just looking at x displacement and how that changes over time. So at time t equals 0, we can see that our x displacement is 0.87. What happens as time progresses? Well, as time progresses, our x displacement changes. And notice what happens. Because we're looking at the cosine of theta, as we're increasing theta, our cosine is getting a bit smaller until eventually it hits 1. If we keep going, now our x displacement is in the opposite direction, so it's negative. It reaches a maximum of -1, and then it starts increasing again. And as time increases further, we can see that our x displacement is giving us a rather beautiful, well, sinusoid or cosine, depending on the phase angle that you pick. But the one that we've picked it's a cosine. So it can take a little while to see how all of this is linked together, but I suggest that you play with it a bit. You can play with the app and see the link between the displacement on the x-axis and how that changes over time and how that ends up giving us a cosine. All right, So we can see that if we're looking, in this case we were looking from the bottom up at the x displacement, and if we plot that over time, we see that what we really have is some simple harmonic motion, except with a cosine instead of a sine, and an alpha instead of a phi 0. But let's see what we can do about that.